Okay, if we can start with the definition of a quantum data center, how would you define it, and how does it fundamentally differ from what we might call traditional data center infrastructure?
So I guess today the quantum data center really is the current classic data center with some cuckoos in the nest, as it were. Because if you think about the state of quantum computing today, it's very, very nascent, very, very early in its journey. And while we and others have been involved in getting, should we say, quantum computers deployed in a data center, in reality, all we've done is picked up current bits of research equipment or early stage quantum computers and physically placed them inside that data center. So we've basically said to make our product work in the companies that we're working with, people like Oxford Quantum Circuits, to use the public ones that we're working with, we've literally picked up some of their research fridges where they've had some of their Toshiko processors in. We've put them into existing data centers in Japan or New York or the UK. And we've said these are our facilities requirements. Now, the interesting challenge there has been that some of those facilities everyone was very comfortable with, power, air. But when we said we'd like to have some water in your data center, they went, water in a data center, I'm sorry, we don't do that. So we ended up going through a few challenges to get those integrated. But in reality, it's still today's data center with a small early quantum computer plugged in next door. So I don't think it's changed yet.
Okay, so longer term, I mean, I'm slightly surprised maybe because, as I'm sure you're aware, liquid cooling is the one of the big trends in data centers. You'd have thought perhaps people were comfortable or at least more receptive to the idea of liquid coming to data centers. But what other challenges are there, if you like, over time, integrating quantum into a classical data center, or do you have to, start from the ground up eventually?
So that's a like you. I mean, my background's semiconductor industry, so I'm very used to big facilities, big issues, yeah, and actually saying, well, if I need a bit of facilities to make this work, provided I've understood it, understood the risks of introducing it, have put in the controls for managing it, there should be nothing that I'm worried about. But when we've been doing this work with people, permitting for things that are not currently on their list of approved utilities has definitely been an issue. So for me, I go, if I'm a data center, I'm quite used to having compressed gas for the fire control system. But then I've got this other thing called compressed helium, and they go, oh, that's different. Or we'll have to go through a permitting issue to address that. But ironically, once people actually understand what these things are, and actually they're very, very similar to what they already need, a lot of these problems start to go away. So I think the first challenge at the moment really is education. So, and really, I think this also depends on the modality of qubit. So if you're an optical qubit and really all you want is power and a bit of cooling, then a data center integrator is going to go, well, I recognize what you look like. You look like a rack. Therefore, you can go into a space that I'd normally reserve for a rack, and therefore no major drama. If you're a large dilution refrigerator and you're coming in with a whole bunch of paraphernalia, which includes some large mechanical frames, requirements for vibration isolation, and then you've got some of these new fundamental things like, oh, you want some liquid nitrogen and you've got some helium compressed in your system. They're different. We just need to understand what they are. The integration takes a little bit longer, but practically speaking, a lot of the fridge people said, oh, we've got a lot of power. We're bringing a lot of power into this space. But when you think about a data center, racks and data centers are bigger consumers of power than the current sort of small dilution fridges that are being used to deploy these things. So data centers in some regard are going, what's your problem? We've got more air conditioning than you ever want. We've got more cooling overall than you ever want. So in reality, it's not the big concern that everybody perhaps might think it is. It's just familiarity at this moment. Now,
So, oh, sorry, yeah, carry on.
oh, but going forward, perhaps that's a very different question.
Yeah, and in terms of I mean, the clearly the AI boom's happening at the moment. So, are you suggesting that at least in the short term, setting up a quantum data center, as it were, is perhaps even easier than the AI? Because obviously the AI is putting a lot of new demands on data centers, but it sounds as if quantum computing, at least in the short term, isn't perhaps that troublesome, shall we say?
From my perspective, I would say from the ones that we've been involved in, it's not that troublesome. It's just about creating that familiarity. In reality, why do people talk about a quantum data center in the short term? purely and simply because to actually own a fridge, yeah, to actually have all the people that understand how to run that fridge, to have the team of scientists that can actually characterize and calibrate the qubits, yeah, to make sure that thing is operational, is actually quite a big team sitting behind it. Whereas if you actually outsource that to somebody else by putting your quantum computer in a data center, the access model, it pretty much looks like the current access model that everybody's really, really comfortable with via the cloud. So for me, the whole point of using the term quantum data center just says to people, your access model is what you know. Yes, there's this new slightly quirky thing called a quantum processor, as opposed to the classical processor you're used to. But if somebody else is dealing with the stack and the integration of those two things, and actually all you're worried about is getting a little bit closer to understand how you might learn to use this thing, and start thinking about your algorithms and the processes you might actually want to pump through this quantum computer in future times, making that very, very familiar means people are more comfortable giving it a go than they would be going, well, how do I assemble this team of specialist PhD scientists to make this quirky and slightly unrobust thing work? So to me, that's why I think data centers is quite a useful way of talking about it, because it just says, we know this.
Yeah, and I was going to ask, and you've, I guess, sort of semi-answered it, but in terms of the cloud-based access to quantum hardware, is that the sort of the future in terms of accelerating adoption, as you explain, yeah, gives people a chance to, and if that is the case, what does that mean for data center service models? Is there some
That's
implication
a,
there?
yeah, that's a really good question. I think for the average user, and even for a lot of commercial users, I think the cloud-based model is going to be a thing. Unless you're a true out-and-out specialist, like a government, a national capability, or you're a sort of large, and I mean very large industrial tech company who wants their own thing for their own reasons. The cloud compute model, I think, is going to be the way that this gets done. I mean, once upon a time, I'm young enough to remember that when I first started doing CFD, computational fluid dynamics, years ago, I used to have to walk up to my Cray mainframe and start actually specifically programming it on an internal network. The cloud didn't exist. These days, most people wouldn't even think about doing that. They just port the whole thing up to the cloud and go, right, somebody up there has dealt with the compute side of this. I've got all the power I need. I've just got to pay for play. So I think that is absolutely going to be the model for quantum as well. And the fact that somebody will sit there and go, for the problem that you've given me, we will work out for you which proportion of this gets put onto quantum, which portion of this gets put onto classic high performance compute, is going to be the way it works. And people talk about the quantum data center, but in reality, it's always going to be a hybrid data center. There is quantum computing will always need a proportion, or sometimes a very large proportion, of classic compute to solve the problem. Now, I'm not an expert in this space, but I've been very fortunate to talk to a lot of people that are doing work up and down the stack, and their answer, regardless of the qubit modality, has been pretty much consistent. So I think we know what the model looks like, even if we don't know what the quantum computer looks like yet.
Yeah, so and sort of longer term, will anything change? I mean, if momentum, yeah, is behind quantum computing, can we foresee a time when, if not, a data center totally dedicated to quantum, it might be the the reason why the data center is built, and then there's an element of classical computing, as you say, that's required. Just your thoughts, I suppose, as to how far this momentum will take quantum.
I think there will definitely be quite a significant change, and I say that and purely simply because, as mentioned earlier, quantum computing is currently very, very nascent, and it doesn't matter whether you're an optical qubit or an NV qubit or a spin qubit or a superconducting qubit. We're all very, very early in the journey here, and every single one of those has still got some quite significant science and or integration and or scaling problems to solve before you actually go, here is a genuine quantum computer. Now, if I take the current most invested in space, and I'm sure some people will say, well, we're the biggest quantum computer company, but let's be really honest. The people that are spending the most money on this at the moment are the big tech firms. Yeah, and we all know the IBMs, the Googles, the Microsoft, the Amazons, they're all spending literally hundreds of millions of dollars solving their problems each year. And most of those investments are going into qubits that need cold. Yeah, so either spin or superconducting qubits. Therefore, if you assume that you're always going to need a cryogenic solution, to deploy some of those large qubits, I think what you start to think about then is some very, very different cooling requirements in the future. Today, all these small fridges use small mechanical coolers known as pulse tubes. You plug one in, each pulse tube needs about 10 kilowatts of power. And you go, well, I'll just put multiple pulse tubes in, and that's okay. And you go, well, data centers could easily handle 100 kilowatts, a gigawatt. Yeah, that's the sort of power numbers they're already using. But when you think about the way that these bits of technology for the qubits are going to go in the next number of years, the actual power density inside the cryogenics required to run those systems is going to change. And that means the current mechanical coolers probably don't work. And people are already starting to talk about articles in the press about using bulk cooling. And by bulk cooling, we mean large cryogenic plant, either liquid helium or liquid nitrogen. Now, they are not going to be easily installed in a current data center. Yeah, we're talking about needing a very, very large 100, 200 million pounds worth of cooling capability built on the side of your current plant. And when we think about the integration of those types of capability into a data center, you can definitely see that the current buildings and the current infrastructure probably don't scale once you start deploying quantum computing at scale. And you're definitely going to have to think about what does a new hybrid quantum and classic data center looks like, purely and simply from a facilities point of view. And I think I mentioned earlier on, people got to get used to new facilities. Yeah, so today, if I said to somebody, "Hi, I'd like to walk into your data center, yeah, in Slough or in New York, and I'd like to put some high pressure helium running all the way through your building," I know the answer to that would be no. Whereas if you sit down and plan these things from the bottom up, and people get very used to how this is going to work and the separation between HPC and classic, you can see how that proper integration being thought through gets everybody comfortable. And more to the point, we know we'll create an optimized hybrid data center for the future. Now, to the user on the outside, they don't care. It's still something they access via the cloud. It's still exactly the same. But for the engineers behind the scenes, yeah, we've just done a very, very different thing in 2030 onwards, perhaps, than we've done in 2023, 24, 25, when we put these nascent quantum computers into existing data centers. So absolutely, I see a big sea change coming, and it will need to be planned and it will need to be thought out.
And in terms of where they might be, are they latency? Are there any of the applications they will run latency sensitive, or a bit like the AI large language models? Can they be? The good news is they don't have to be in London and Frankfurt and all these, overpopulated areas. They can be sort of in the middle of nowheres because they're not, I say, latency sensitive, or is that not the case?
No, I think that the integration testing going on between high performance compute and quantum computing is starting to think about latency at the moment. And some of the partners we're working with are starting to do testing going, well, how much latency can I have between this and this? Yeah, and how far up the stack do I separate the problem? And can I actually send some of it just here and just there? Or do I actually need to come further down the stack and actually separate it out at a much lower level and have proper integration? I think we're doing the experiments to learn all that, or start learning all of that at the present time. But I think the answer comes down to we will need an integration to be close. I think there is going to be a latency question based on what people are talking about. But I think that's internal to the data center. So to your point, I don't think you need to say, if I'm the City of London, it's got to be in London. Yeah, it's cloud access. As long as it is where it is, and as long as it does what it does, and as long as I get the answer back in a timely way, I could put it anywhere I like. That's the cloud model. I think it still scales.
And in terms of the industries most likely to benefit from the quantum data centers, I don't know, finance, healthcare, and how close are we? Because again, I see, I'm sure you keep a close watch on it, but I see various press releases telling me things, but in terms of real world use cases, where are we at the moment as well?
Oh, that's a great question. So I think take some really simplistic cases like quantum random number generation. That's should we say, a very simple application. It's good for security. Yeah, that's happening now. People are already offering that service. You've got people that have started doing, in the banking side, some early simulations on using Monte Carlo on quantum compute. And they're saying, well, even now it's got a little bit of a benefit. And even though these quantum computers don't work very well, and most of them are simulated rather than actual, Yeah, they're still going, well, we can already start to see how the benefits of this is. For people doing real proper simulation for the drugs discovery, yeah, or for material simulation, we haven't really got a quantum computer yet that actually solves their problem. We're a good stick away from that. But those things for the chemists, the drugs companies, yeah, or the materials companies, the people that start to do effectively weather and mineral simulation, I think we can definitely see that there will be huge benefits in that. I mean, I'm from a research background, and people spend lots of money and lots of time working through and characterizing materials. Imagine if you can actually take the use cases down significantly in terms of the parameters you might want to test. We're already seeing the benefit of some of that with AI, and that's just with AI being cleverer about the sifting of the options, and that's without really being able to do much of the simulation inside it. Imagine you've got that hybrid approach where you've got the AI doing the thinking and the quantum doing the analysis underneath it. You can see that's going to be huge, but I think we're a good few years away from that. But that doesn't stop us getting excited about it, and it certainly doesn't stop us wanting to invest the money and work hard to get there. And I've, as an engineer rather than a scientist in this space, these are the tools that 20 years ago, when I was still doing the actual sort of on the ground work, I'd have been really excited to get my hands on. Yeah, it just turns out that I'm probably going to be a couple of decades too old by the time it turns up.
Unfair. And is there any particular significance in launching the quantum AI data center in New York, or was it just you ended up there, or as I say, is there particular reasons behind why there?
So I think that this is about partners. Yeah, I mean, we ourselves do not deploy quantum computers. We're a cryogenic solutions provider to people like OQC that do. Now, why put them in interesting places? Um, Tokyo, very good place because again, it's right in the middle of Asia. It's a place where you've got a large financial and industrial base. Yet people go, wow, let's get involved in quantum computing. Again, same with New York. It's very, very public. It creates very, very good PR. And hopefully it creates the right engagement with people saying, you know what, this technology is not just near term, but actually physically close by. So I think a very clever selection of places creates the connection with people to wanting to get involved with these things and say, you know what, if I don't get involved, I will miss out. I will not be an early adopter. And I will share a statement made to me by the leading in computing from a large multinational. And he said, right now, he said, we are very, very interested in the algorithms for quantum computing, just as we are with HPC. He said, from an HPC point of view, we don't think about hardware really. He said, because every 5 or 10 years, we know we're throwing away what we've got, yeah, and we get a whole new set. So in reality, the thing that is where we invest all our money is understanding the solutions and the algorithms, yeah, and we just assume we get better and better hardware later. And he said, that's how we're treating quantum. We know right now we need to understand that there will be a thing. Yeah, we need to understand how our algorithms will be constructed for that thing. But in reality, we know that the ones we have today are not going to be very useful. But provided that we understand how they work, as the technology gets better, in 5 years' time, we'll already be well on our journey. And having a quantum computer next to a large financial institution in either London or New York to help that bit of thinking be connected, I think just helps the whole journey get ready. There's no point in people like me making very, very large cryogenics. And we put out a great post last week showing how big some of our cryogenics are for some of those larger companies at the moment. There's no point in us doing all this work if nobody's ready to receive the technology. And I think that's the where the cloud compute piece and the access to quantum data centers comes in. It's just getting people in that mindset. I don't think it's any more than that, really. Yeah, we're all excited, but excited about what? Until you've tested, until you've kicked the tires, until you've tried pulling the thread, you don't know whether it's for you.
Yeah, and perhaps just expanding on that in terms of the sort of international and cross-sector collaboration, and how important, because I guess obviously some people are looking to get a competitive advantage and maybe aren't wanting, but overall, is there a pretty much an international collaborative community realizing that it's good for everyone to put your heads together and come up with solutions, and if that is the case, are there any particular partnership models do you think that are working better than others? Just I suppose, yeah, your thoughts on the collaborative process.
Right now, you've got some companies, big and small, that are saying they own the whole stack. I think if you're an IBM, yeah, or you're a Google, or you're one of those really, really big companies and you've got the financial clout, I think you could claim to own the stack. If you're a smaller, like mid-scaler, you just haven't got the physical infrastructure in your organization to own everything in the stack. So therefore, I think the collaboration model is absolutely critical. If I think about where progress is being made, you've got small qubit developers connecting with people that are doing surface code to try and improve the error rate. You've got other people starting to work on algorithms. You've got other people starting to talk to data centers about integration. Every successful thing that we've been involved in is actually multiple companies, each of whom are bringing a small proportion of the answer together and going, yeah, we've made an incremental gain. Here's a step. Here's a step. Here's a step. It's all about focus. I said earlier on that there are lots of science challenges to still be solved to bring this stuff through. And I think that key thing about going, know what you're good at, deliver what you're good at, partner with somebody else who's equally good at something that you're not, I think is how this gets done, rather than one individual or one company going, we've got everything. I don't think anybody's got everything. So partnership models is absolutely it for me.
And in terms of perhaps a final thought, you've explained how you see the quantum data centers evolving, but is there any advice you can give to today's data center operators in terms of any preparation they can be doing for that future, or do they just need to sit patiently on the sidelines until developments happen and they know how to respond? Just your thoughts, I suppose, as to what they should or shouldn't be doing right now.
I would absolutely say come and research the technologies. Yeah, pick the modal, look at the modalities, whether it's, say, the opticals, whether it's the NVs, whether it's the superconducting, or whether it's the other sort of cryogenic ones, and come and understand what the infrastructure is to run the environment that will host those bits of quantum computing. Yeah, the models will tell you if you're room temperature, then you just need perhaps more power and better cooling. But actually, some of the sensors around those systems also require some cryogenics. If you're a superconducting qubit, it's great to go and look at what a fridge that's running today's superconducting qubit is, but go and read the articles on bulk cooling and what you will need in future, and actually start thinking that in 3 or 4 years' time, the next data center you build might need some very, very different facilities. And therefore you will need to lay it out differently. So I would absolutely encourage anybody in that space to actually come and start doing their research, talking to the providers and going, right, what is it? If not, you won't be the first one and you will be left behind. And we all know this is one of those games where being first is going to matter.
And just from your own perspective, you sound very optimistic. I mean, you say obviously there are still some technical challenges. Are you sort of confident that people are aware, how they will be solved over time? So it's just a question of time, or are there some things that are sort of, snookering people at the moment, if you like, and therefore it's not certain how quickly, solutions will be developed?
So I'll be very selfish about my own interest, the superconducting qubit modality. If you'd asked me that question 4 years ago, I'd have gone, we could be a long way away from actually solving this. But when I look at the progress that people have made on things like qubit latency, and also the error correction models, in the last 18 months, I think some really, really positive things have happened. And I can definitely see now a route to making some quite significant progress over the next few years rather than decades. And I think two areas that I'd highlight there. One, the quality of the qubit, yeah, and the quality of the error correction, I think has definitely made some quite significant progress. The other is scaling. Today, all of those qubits, superconducting qubits, are connected by wires that have to go from room temperature down to fridges. That's a non-scalable solution past maybe sort of 5 or 10,000 physical qubits. But I'm seeing some really interesting work where people are using cryogenic CMOS to actually start becoming the multiplexing and the interfacing to those quantum chips. That is absolutely part of the building block. And if you watch that space and you go, I can see companies solving that interconnection problem, that's the point. I think you've generally got a combination of qubit technologies and scaling technology, interface technologies that says this is coming to a data center near you soon. Yeah, and that's really when you go, no, I'm really excited. 2 years ago, couldn't see that starting to happen. Based on conversations in the last 12 months, absolutely starting to see that starting to happen. Um, when, I think, is always an interesting question, but I think it's now definitely a when in years, not if in decades.
Final question, promise. You mentioned there, the same. So, is the semiconductor industry equally invested and excited, and also slightly uncertain? You've got sort of data centers at one end of the supply chain, and then like the semiconductors the other. Where are they at, if you like, in terms of buying into this or and understanding this future?
So when I first came to QD Oxford, I asked the question, so when you fabricate your qubits, how do you do it? And I was walking around university labs and I looked at what they were doing and I went, it's no wonder your qubits don't work very well. Your fabrication techniques are atrocious. I come from the semiconductor industry. I'm used to ULSI integration. What I'm seeing is as people are getting closer and closer to using what I would call production ready fab capability, funny enough, the quality of their qubits are getting better. At the moment, there's no fundamentally new techniques to fabricate that are required. Yeah, but there are certain node sizes that the foundries already have, which have been qualified for running cold, as it were. And perhaps those are the ones that people are going to be most comfortable with earlier. So in terms of chip quantities, I don't think the semiconductor industry is too bothered yet. In terms of specific capabilities for certain films, yes, we'll definitely need to see perhaps a little bit of growth in some foundry models to deliver that. But in reality, there's no new techniques or tools that that industry will need to develop. It's just a question of when it becomes valuable enough to want to do.
Excellent. Been brilliant to chat, and thank you so much for explaining what is going on I say everyone's looking at AI right now, but clearly quantum is coming up fast and it's an exciting future. So Matt, really appreciate the time and the
No,
discussion. Thank you.
thanks, Phil. And I say, a view on the world from a very certain point of view.
No, fantastic. Thank you.